Hello, welcome to Chapter 10, where we're going to continue talking about acids and bases and their equilibria, but now we're going to extend it from a monoprotic system to polyprotic systems. So things that have multiple protons that can be donated or multiple proton acceptor locations in the molecule. Polyprotic acids and bases are really important for lots of different areas. Many different examples. Of course, we have several polyprotic acids and bases that are used commonly in chemistry, things like phosphoric acid, which has 3 protons, carbonic acid, another one that shows up quite a bit. We also have sulfuric acid, that's a strong acid, it's polyprotic. But one of the most relevant examples of a polyprotic acid or base is amino acids. So these are the building blocks of the proteins that make up part of our body. For any of you that are taking biochemistry or are planning on taking it, you'll learn all about amino acids and how they link together to form peptide chains that make proteins. So amino acids have the general sort of structure like this, where they have an amino group, a carbon, some side chain here R, and then a carboxylic acid group on the other side. So we have one proton that can be lost here, and this is actually a proton acceptor site here on the amino group. And some amino acids even have additional acid or base constituents on this R group on the side. So understanding polyprotic acid-base equilibria is key to understanding biochemistry and understanding how this works. So what we're going to do in this chapter to understand polyprotic acid-base equilibria, we'll start with the simplest case of a diprotic acid. And consider how we would treat this, how we would find the pH values, similar to what we did for monoprotic species, and then we will extend to polyprotic, right? Maybe a triprotic, or we won't. You can have things with a lot more, but we're going to stick to just a few protons on the acid or base. So as we're thinking about a diprotic species, we're going to look at one specific example as sort of our test case, which is alanine. Alanine is an amino acid, specifically one where the R, the side group, is a methyl group. So we don't have any additional acid or base constituents in that R group. All right, and so we can look up for alanine what are the Ka values for the two different protons. So we have pKa for the carboxylic acid group is equal to 2.344. As we'd expect, that's a fairly low pKa. It is an acid. And the pKa for the amino group, which again is listed as the acidic form, when you look it up in the table in your textbook, is 9.868. So significantly higher because the amino group is a base. It's a proton acceptor rather than a proton donor. Okay, but there are 3 different forms our amino acid can take. So we can have the fully protonated version, H2A+, will represent alanine as A. Right, so again, the fully protonated form, H2A+, where we have the positive, right? It's positive because there's NH3+ group, the amino group is protonated, and there's also a proton on the carboxylic acid. That proton on the carboxylic acid can be lost, and then we form the intermediate form, HA. And then we could lose that proton that's on the base and form the negatively charged ion, where we have A-. We've lost both protons. All right, so we have the acidic form, the intermediate, and the base form, or basic form. And if we want to write out the equilibria that are going on here, right, we can write out a Ka and a Kb value for each of these. So if we have H2A+, that will be in equilibrium with H plus A. HA. and that is our Ka1. That's the convention that we use here, or sometimes we'll just write K1. And then HA can subsequently also have its own Ka value plus A minus, and that's Ka2 or K2. That's the numbering convention we use for this. Or we can write this in reverse for the basic forms. We can take A minus plus water will be in equilibrium with HA plus hydroxide, and we call that KB1. And we can, of course, take the intermediate form, HA plus water, can take the proton from the water, and we get H2A plus hydroxide, and that we call KB2. So I'll stop here for this video. In the next video, we're going to look at how do we calculate the pH for these different forms of the diprotic acid that we have.